Does information have a mass? At first glance, this might seem like an odd question. When we think of information, we often visualize it as an abstract entity, an ethereal substance that exists without physical weight. The information in a book, for instance, is not something we can weigh on a scale. It's the patterns, the data, the knowledge that the book contains. It's not the paper and ink used to express this information which are the tangible, measurable entities. So it would seem that information, being abstract and intangible, does not possess mass. It exists in our minds, in our conversations, in our databases, but you can't put a piece of information on a table and watch it tip the scales. So in its most basic form, information does not have mass. However, when we delve into the world of physics, things start to get more interesting. In the realm of physics, particularly when we consider Einstein's theory of relativity, energy and mass are intimately linked, as expressed in the famous equation E=mc². Now, processing and storing information requires energy regardless of the form it takes. So, if we look at it from a rather abstract and indirect standpoint, we could argue that information is, in some way, linked to mass. This idea gains momentum when we venture into the enigmatic world of black holes. According to Stephen Hawking's theory, black holes gradually evaporate over time, emitting what's known as Hawking radiation. This process could theoretically lead to the complete obliteration of information. But here's the catch. This clashes head-on with a core principle of quantum mechanics, which insists that information can never be lost. This conundrum, known as the black hole information paradox, has sparked a multitude of theories, including the intriguing notion that information may possess a sort of mass or physical property that is conserved. Now let's take a quantum leap into the realm of quantum mechanics, where information is a fundamental player. Here we deal with quantum bits, or qubits, which, unlike their classical counterparts, can exist in multiple states at once. While the qubits themselves, being quantum states, don't have mass, the systems that manipulate them, like quantum computers, do require physical matter and energy. So, within the realm of advanced physics and quantum mechanics, the concept of information having mass starts to emerge. However, it's important to note that this is not mass in the everyday, tangible sense. It's an incredibly tiny theoretical amount that's more a subject of fascination for physicists than something that has practical implications for most of us. But in the grand scheme of things, it's these minuscule, seemingly inconsequential details that often hold the key to unraveling the mysteries of the universe. Moving into the realm of computing, there's another interesting concept to consider: Landauer's principle. This principle, named after physicist Rolf Landauer, posits that erasing information in a computing device incurs a minimum energy cost. Now you might be wondering, what does erasing information have to do with energy or mass? Well, every time we delete data, the information isn't just disappearing into thin air. According to Landauer's principle, it's being transformed into heat, which is a form of energy. And as we've learned from Einstein's theory of relativity, energy and mass are two sides of the same coin. So, in a very abstract and indirect sense, information is tied to mass. However, it's important to note that the mass involved is so tiny, it's almost entirely theoretical. So, while we can't exactly weigh information, Landauer's principle further strengthens the connection between information and mass, albeit in a very subtle and theoretical way. So, does information have a mass? We've journeyed through the abstract nature of information, dove into the depths of physics and quantum mechanics, and even touched upon Landauer's principle. We've seen that information in its purest abstract form doesn't have mass. It's the invisible, intangible patterns and data that we assign meaning to. Yet, when we venture into the realms of physics and quantum mechanics, the lines blur. The physical representation and processing of information do involve energy, and through Einstein's iconic equation E=mc², we can see an indirect relationship between information and mass. The black hole information paradox and quantum information further complicate the picture, suggesting that information may have some kind of physical property. Landauer's principle also hints at a tiny, almost theoretical mass associated with the energy cost of erasing information. In the end, while the idea of information having mass is largely theoretical and of little practical significance, It's a fascinating concept that challenges our understanding of information, mass, and the universe itself. Have you ever wondered what the universe is made of? Today we're exploring an intriguing topic, the comparison of matter and information. Allow me to introduce you to these concepts. Matter is anything that has mass and occupies space. It's the air we breathe, the stars in the sky, and the very atoms and molecules that make up our world. Governed by the laws of physics, matter is tangible and can be experienced through our senses. Unlike matter, information is intangible. It's a way to describe the arrangement or structure of matter, or more broadly, the state of a system. It's the words in a book, the code in our DNA, and the patterns that dictate the world around us. Understanding both matter and information is crucial for grasping the complexities of the world around us. Now that we've described matter and information, let's compare and contrast these two fundamental aspects of our universe. Matter is the physical substance that occupies space and has mass. You can touch a rock, feel the wind, or hold a glass of water. Information, however, is an abstract concept describing the state or structure of matter. You can't touch the words in a book, but you can touch the pages they are printed on. Next, let's talk about conservation. In a closed system, matter is conserved, meaning it cannot be created nor destroyed, merely transformed. Conversely, information behaves differently. It can be replicated, altered, or even lost over time. At least it can be made more difficult to read. Think about how quickly a file can be copied and shared online, or how easily it can be deleted. Yet despite these differences, matter and information are remarkably interdependent. The structure of matter can convey information. Consider the grooves on a vinyl record. Similarly, information often requires a physical medium. Think about the hard drive in your computer, storing countless bits of data. From a quantum perspective, the relationship between matter and information takes an even more intriguing turn. In the realm of quantum mechanics, simply observing matter can change its state. This intertwining of matter and information is a fundamental concept in quantum theory. Lastly, let's consider entropy. In thermodynamics, entropy is a measure of disorder. But in the context of information theory, it measures uncertainty or the amount of information in a system. This creates a fascinating link between matter and information. As matter becomes more disordered, the information it contains becomes less predictable. While matter and information are deeply connected, they are fundamentally different, each playing a unique role in our understanding of the universe. And by understanding both, we can better comprehend the complexities of the world around us. One might question the statement that information can be easily lost. Doesn't quantum mechanics suggest that information is never lost? This is a great observation that leads us to the quantum no-cloning theorem and the black hole information paradox. Let's start with the quantum no-cloning theorem. This principle states that it's impossible to create an identical copy of an arbitrary, unknown quantum state. It ensures the uniqueness of quantum information, prohibiting its free replication, unlike classical information. Now let's step into the realm of the mysterious with the black hole information paradox. This paradox arises from the idea that information cannot be destroyed, yet it seems to disappear in a black hole, a contradiction to our understanding of physics. These concepts hint at a form of conservation of quantum information, adding layers of complexity to our understanding of information in the quantum world. In recent years, physicists have proposed various solutions to this paradox, suggesting ways in which information might be preserved, such as the holographic principle or the idea that information is somehow encoded in the Hawking radiation. However, there's no universally accepted solution yet. As we've seen, comparing matter and information reveals intriguing insights about the nature of our universe. Matter, tangible and governed by physical laws, forms the concrete framework of our reality. Information, intangible and mutable, describes the arrangement and state of this matter. Together, they interweave to shape the world we perceive. In the realm of quantum mechanics, these concepts blur and intertwine in fascinating ways. The quantum no-cloning theorem implies a certain conservation of quantum information, challenging our understanding of replication and transformation. Meanwhile, the mystery of the black hole information paradox continues to fuel heated debates among physicists. In the context of quantum mechanics, information is considered to be conserved. But how this works, especially in extreme conditions like black holes, is still a subject of ongoing research and debate. The quantum realm challenges our classical understanding of concepts like information conservation, leading to new and exciting hypotheses in theoretical physics. These explorations remind us that our universe is a complex tapestry of matter and information, of tangible realities and abstract descriptions of physical laws and quantum uncertainties. Understanding the interplay between matter and information allows us to better grasp the complexities of the world around us.